Alright, so this will be the new part of this week, and I'm pretty excited to share this stuff with you. I think it's kind of interesting. We're going to look at some mathematical models of epidemics. There are quite a few, and we'll do a couple this week, and we'll do a couple the following week. So we've been playing around with some very light models, regressions, and making some predictions. But those are sort of tinker toys compared to what can be done. And well, let's just jump into it. So the models I'm going to show you, they involve calculus. But we're not going to solve them. We're not going to really do any algebra with them. You're not going to be responsible for doing any of that. But we can still chat about them. Now, this isn't usually done in math, and it's a real shame. And the analogy I like to use is like music appreciation. If you take a music appreciation class, you're going to listen to pieces of music that you can't play not with an enormous amount of practice. You're also not expected to compose them. You're not expected to, play the clarinet piece or the percussion piece or whatever. But you are expected to be able to compare and contrast different compositions, maybe indicate themes in them, or maybe melodies or time periods or whatever. And this is the same in art history, in lots of different subjects. It's expected that you can compare and contrast sophisticated ideas, even if you're not ready to come up with those ideas yourself. So we're going to do that here with mathematical models. I want to show you some heavy machinery, but you're not going to be responsible for doing any sort of calculus or any such stuff. So let's take a look. And part of the goal here is when we get through with this and next week's is I'll show you a couple abstracts from current research. I mean, stuff that's been published in the past week or so that's trying to understand the coronavirus outbreak. And sort of my point is that you'll be able to look at this abstract from a peer-reviewed journal and say, oh, sure, that makes sense. And it's not that much of a stretch, actually. So these are the some of the models we're going to be looking at. This week, we're going to look at the first three, the SI, SIS, and SIR models. So here's how this works. In all these models, S is for susceptible and I is for infected. And we're going to start with the simplest model first, the SI model. So what this model assumes is that you have two types of people in your population. People that are susceptible to disease, and then people who are infected with the disease. And that's it. And you can think of these as compartments. This is actually an example of a compartment model. One compartment is of susceptible people. The other compartment is infected people. And there's a number A that determines the probability of moving from one to the other. So sometimes A is called like a transmission coefficient or transmission parameter, or it's the probability of becoming infected due to exposure. So it's kind of, any of those are fine. So these are differential equations. But here's what this prime means. You see this prime? S prime means the change in S, the change in the number of susceptible people. Now what do we have over here? A, that's the probability. S is the number of susceptibles. I is the number of infecteds. N is the size of the population. So basically, if there are a lot of infected people, that makes this thing bigger. If there's a lot of susceptible people, it makes it bigger. And then depending on the population, that scales it. What's really important is that A is positive, S is positive, I is positive, N is positive. And so this negative sign means this whole thing is always negative. That means that the change in S is negative. What does that mean? Well, that means you're going to have less and less susceptible people. People become infected. And then over here, notice it's the same expression, but with no negative. That means that the change in I prime, the change in the number of infected people, infecteds, as epidemiologists call them, is positive. When change is positive, it's increasing. So what this model says is, right from the get-go, you're going to You're going to lose susceptible people and gain infected people. In an illness, this might model as herpes. If you contract herpes, you keep it. There's no getting better. That's it. You're done. Now, right? You see some fancy equations. There's some letters. Oh my God, it's finally happening. No, we're just looking at them. It's just like a piece by Brahms or Chopin. We're listening to the music. We're not going to have to play the music or analyze the sheet music or something. We're just looking at this and we're chatting about it. Right? So here I just provide some more information that I was already telling you about. There are a couple other assumptions here. So we would start with some number of infecteds, and really infecteds is what they're referred to here. So you assume quite often that you have one, but you could do others. So you assume you have some population, and one of the population is infected, and they're going to proceed to infect everyone else. And there's a well-mixed population assumption. So the idea in all the models we're going to look at is that everyone eventually bumps into everybody else, which is certainly unrealistic if you were looking at a large country like the United States. Not too unrealistic looking at smaller populations, for example. Right? Still concerned? Still concerned? Right? Somebody has too much time in their hands. That would be me. So here's a graph. So this top bit here is the population size. This blue curve is susceptibles, and the red curve is infecteds. So I imagine you start with 100. Could be 100,000, it could be 100 million, whatever. But 100, and then you start with that down here. The red, you can't see it, but the red crosses at 1. And so you start the clock. Infecteds increase till they're saturating the population. Susceptibles decrease, they cross. This is an infection rate curve. So orange is the infected rate. That's funny. It really was green when I graphed it. I don't know why it's blue now. But this hump here, this is that curve everyone's talking about it. In coronavirus, flattening the curve or whatever. And this is the epidemic curve, this red curve here. But this is not a good model for coronavirus, as we'll see, because this assumes that you keep the infection. You do not recover from the infection. If you click on this, you can play with this graph. You can change the transmission to see how that affects. So that's the value A. Actually, might be kind of fun to do that. So there's only one parameter in this model. That's the model A. And so if you were to click on that, oops, you can see what happens. If you increase A, right, then it spreads faster. If you decrease A, so the probability decreases, it takes longer. But again, notice that in this model, eventually everyone becomes infected. There's no avoiding it. It's a pretty simple model. All right. So overview, it's a well-mixed population. There's no immunity gain. Everyone gets infected and stays that way. Birth rate 0, death rate 0, and the disease results in no deaths. Population remains constant. Okay? And this transmission remains constant also. All right, next model, SIS. So what does the S mean now? What the S means now is that after you're infected, you can recover, but you don't gain any immunity through that. You just go back into the compartment of susceptible folks, right? So the common cold is a good example. So after you recover from the common cold, you are not immune from getting the common cold again. So, and there are many other illnesses that follow this pattern. So you have folks that are susceptible and folks who are infected, but they can and do recover. So this adds an extra letter, B. B is controlling how quickly folks recover from this illness. which means there's a subtraction here. So the rate of change of infection is decreased by people recovering. And the rate of change of the susceptibility is, right, this is a negative number, so susceptibles are decreasing, but there are people who are getting better. So you can interpret the parameter B as how quickly folks recover from being infected. Notice also there's no immunity gained through exposure here. And 1 over B would actually be the length of time to recover. So that would be the incubation rate. So 1 over B would be the incubation rate, something we talked about last time. Here's another curve. So this one's a little different. You don't necessarily infect everybody, and that's because as people are being infected, other people are recovering and going back into the susceptible pool. So what happens in this model is there's an equilibrium state. We have susceptible folks here, and this is the population up here, this dotted line, and so they become, more and more folks become infected. That's the red curve, but the red curve never reaches the full population because there are people who are becoming better. And the susceptibles never go to zero. There's always some people who are susceptible who become infected, but the infected become susceptible. And so over here we have this equilibrium where, yeah, there are always some people, essentially there are always some people with a cold, and there are always some people without a cold, and that just continues, forever. Again, notice there is this little hump. This is the rate of infection down here, this blue curve, and so this is rate of infection kind of peaks right about here, and then it goes down until the rate of infection is 0, meaning that, and what's happening there is just as many people are getting infected as are recovering. And again, you can click on graph and play with the model. So summary, SIS has the same assumptions as SI, except the infection's not permanent. You can return to susceptibles to be infected again. Not everyone becomes infected. And the parameters A and B are constant, still constant. All right, next model, SIR. So the new letter R is for recovereds, and R prime is the change in the number of recovereds. So diseases like chickenpox and the measles are well described by this. There are people who are susceptible. They have a probability of becoming infected. That's controlled by A. They recover. That's controlled by B. And then they gain some immunity. So in this case, everybody in the recovered compartment can no longer be infected. They have permanent immunity. So chickenpox and measles are good examples. Once you're immune to them, you cannot contract them. So we have an extra equation here, and it's really very similar to what we just had. Our infections are reduced by the fact that people can recover, and then those people who recover go directly into this R prime equations. B and I are positive, so the number of recovered people is always increasing. The number of susceptible people is always decreasing. And then infections, well, let's see what happens with that. We'll talk about COVID-19 and immunity a little later on. It is believed, though unknown to some degree, whether people are immune after having recovered from COVID-19. But COVID-19 is a part of a type of part of a group of viruses called coronaviruses, and apparently those do bestow immunity usually, though it wears off. All right, so I want to connect this, and we're going to do this more the following week, but I want to connect this back to R naught. So R naught, one of the many ways you can define R naught is actually as a ratio of A times 1 over B. So this A here, the transmission coefficient, and B the sort of recovery rate, together can define R naught. How fast, what's this reproduction number, right? And so an epidemic is mathematically defined when infections are growing. So if your infection rate is growing, so not just infections are growing, but infection rate. And in fact, what you could interpret this to mean that the infections are accelerating. So if you think of infections as distance, if your rate of distance is increasing, and your velocity is increasing, then you're accelerating. So that's scary stuff. So we're just going to do a little bit of algebra. So you don't have to ever do this, but I just want to walk you through it because it isn't that bad. If the rate of infections is increasing, right, it kind of makes sense. If the rate of infections is increasing, then the next line is the equation for I prime. That's greater than 0. At the beginning of an epidemic, the number of susceptibles, S naught, is pretty much the whole population. Everyone's susceptible. That was definitely the case for the coronavirus. And so S over N is roughly 1. Then if you move this BI over, divide by B, you have A over B times I greater than I. This is only true if A over B is greater than 1. So you'll see this, depending on how much you're reading. If R naught has a value greater than 1, that's when we define an epidemic. So what we've done here is a little bit of algebra, derived a condition for an epidemic. If R naught is greater than 1, that means that the rate of infections is positive, right? And so think back to that little excerpt from a paper we read, which estimated a median value for R naught of 2.2 or something. So for an epidemiologist researching that, that would immediately indicate that this virus has the potential for an epidemic, for an outbreak. Right? We'll look more at R naught in the following week when we talk about the herd immunity threshold. That is, how much of our population needs immunity to avoid an outbreak, whether that immunity is gained through vaccination or gained through exposure. Oh gosh, right? That's a good point. I just did a bunch of algebra here. Is this something I'm going to ask you on a quiz? Or am I going to ask this on the third exam? Small pleasures finding Bitmojis. All right, so here's a few graphs. These look a little different because implementing SIR is far more complicated. You can't solve them analytically. All the previous graphs were my own because SI and SIS you can just solve by hand. SIR requires using a computer simulation, and I linked to a couple here that you can look at. And so, in fact, maybe let's just kind of go over and look at a couple of them. They're kind of fun. So we could look at this one, beta and gamma. That's their A and B. So you can do a beta of 1, gamma of 2. That's an R naught of a half. You can see that there's not much of an outbreak here. So infections kind of, these are the recoverers. Blue is the infections. So you start with some people infected and they just get better. That's pretty much it. A few people get infected, but eh. And then if we take and we make these two numbers the same, so now this is an R naught of 1. All right, there's something more serious going on here, right? It lasted a little longer. I mean, the rate, the number of folks who were infected was steadily declining, but definitely more people became infected, right? More people recovered. And now let's start making this R naught bigger, right? So now things are becoming more serious. Now you start seeing this curve here, right? And more people are affected, susceptible, right? Susceptible is going down, recoveries are going up. Let's so if we do 3, this is an R naught of 1.5. Right, pretty serious stuff. Having a peak here, and then what about an R naught of 2? Right, right. And this is getting closer to sort of stuff we're seeing on the White House press briefings. We're seeing this red epidemic curve. We're seeing this infection rate curve. This is the kind of stuff where we're talking about now in the news, and it depends on that R naught, the ratio of transmission to our recovery rate. And so I include some of those graphs here in the presentation, so you can kind of refer to them. There's an R1, there's an R a little bit greater than 1, and there's an R closer to 2. So very different outbreaks. Now SIR still isn't the sort of model we would use for coronavirus, because after you're exposed to coronavirus, you don't develop symptoms right away, right? The incubation rate is somewhere around 5 days. So there's a period of time when you've been exposed, but you're not yet infectious. Current evidence suggests that you're not infectious until you're presenting symptoms. Not sure what that means really for asymptomatic folks. So there's a latency here. So the SEIRS model is you're susceptible, you've been exposed, but you're not infectious. Now you are infectious. Then there's a recovery rate. Now, depending on, we don't know yet whether or not the coronavirus will bestow immunity or not. If it doesn't, then you'll go back to susceptibility. And if it does, then you'll just stay here at recovered. So this is a more complicated model, but again, we're not solving any equations or doing those kinds of things. But we're going to look at this because there's a modified SERI model being used in recent research to try to understand the spread and the evolution of this pandemic. All right, and that's the end today. I know the videos were a little longer this time. Hope you're okay. Hope trying to stay sane and stay safe and healthy. Again, stay in touch with me if you need anything. Best of luck with the practice, and see you next time.